Welcome back! Previously, we understood tensors and dimensionality. Now, we'll learn how to build our first model in TensorFlow. Let's get to our notebook to see what we need to build and train a model. As usual, we start by installing TensorFlow. Once installed, we proceed to import the libraries that we need. In this case, we're importing TensorFlow, Keras, NumPy, and Pandas. When we're done, we can proceed to download the file that we're going to use, which contains our data. That's the iris dataset. Once the values are downloaded, we can proceed to create column names, then load the file into our data frame. We use df.info to see exactly how many records we imported from the file. Note the column class, which is of type object. We can proceed to inspect the top records in our file using df.head. We can see that the class column does not contain numeric variables. However, it contains strings. The computer cannot work with strings, it needs numbers. We're going to convert our categorical variables into integers. We do that by using the next two lines in the cell. First, we convert using the dataframe.asType method. Next, we make use of a Python lambda function to convert our strings into their numeric encoding. Next, we split our data into features and labels. Features are predictors. That is what determines the outputs, and the labels are the outputs that we're trying to predict. Let's scroll back up to show our data. The first four columns, sepal length, sepal width, petal length, and petal width. Our features and our labels are the class column. The goal of this exercise is to try and predict the class that flower falls into based on the four measurements. So the measurements, sepal length and width, petal length and width, are supposed to help us predict what category a flower falls into. Back at the point where we split our data into features and labels, we make use of our data frame and our features as simply the entire data frame with the class column dropped. Then convert it into a NumPy array. Our labels are simply a subset of the data frame containing only the class column. Convert it into a NumPy array. We'll create training and test data sets. Our test data set will simply be the last record in our data. All the others will be used for training. We can see in the cell on the screen that we're slicing our tensors. We can expect our test features to see that it is a 2D array containing only one rule of data. Further down, we can inspect our test label to see that it's a 1D tensor containing the numeric representation of the class of that flower. So far, everything we've seen is something we've covered previously. What's new on the screen is how we start creating a model. We're going to create a Keras sequential model, which is a type of model in TensorFlow that makes use of the Keras API. This is a high-level way of defining a neural network. On screen, we have the code for defining a model, and we define our model as Keras.sequential. Sequential is a method that takes a list, and that list can contain several Keras layers. Keras layer is an implementation of the function that we saw at the beginning of the course. So our hypothesis translates into a layer. It could be a linear regression or logistic regression. In this case, it's a dense layer, and a dense layer is a fully connected layer. For this particular problem with defining our dense layer to have 256 neurons, we give it an activation type of ReLU. There are different types of activation functions, but the ReLU activation is easy to compute. Finally, we need to specify what our outputs would be. In this case, because we have three classes in our dataset, we define our output layer to have 3 neurons. Then we define an activation of softmax for the layer. Next, we need to compile our model. The process of compiling lets us specify an optimizer for a model. The optimizer is an algorithm that determines how our loss is minimized, and essentially, it's carried out using the gradient descent algorithm. Next, we specify what sort of loss function we want to use to determine whether our model is getting better or worse. Because we have 3 classes, we're making use of categorical cross-entropy, and finally, we state that our metric is accurate. After compiling our model, we can proceed to train our model. This is done using the fit method. It takes several parameters, but most importantly, we need to give it our features and our levels. Pox here states the number of times that we would like to go over our training data. In this case, we're going to go over our training data 15 times. Finally, validation split states how we would like to split our training data so that we have a holdout set for validation. In this case, 0.3 means that we want 30% of our data held out for validation. And in the output from that execution, you could see that 104 samples will be used for training and 45 samples will be used for validating. After training our model, we could go ahead and call model predicts, passing in our test data, which is the last row of our data to which we held out. In this case, we're going to get 3 columns representing the 3 neurons that we used in our output layer, and the value in each column is the percentage probability that the column is the answer to the problem. That's the prediction. We could see here our first column is 0.20, second column 0.39, third 0.40. Now our predicted output is going to be a column with the largest numeric value. In this case, our third column has a 40% probability of being right. So at this point, we've trained and tested our model. Let's summarize what we learned. Sequential models let you focus on the real problem, and that's the problem of tuning your model. The process we saw in code is represented on the screen. First, we create a sequential model. This lets us add layers to specify the activation on those layers and connect them to outputs. Then we compiled the model and specified our optimizer and our loss function. Third, we trained the model by providing our training data and specified how many times we want to go over the data for training and what fraction of our data we would like to use for validation. Finally, we got a model and we tried it out. Now that we've come to the end of this section, there's an assignment you could try your hands on. Visit the URL on the left, read the challenge, and download the dataset and give it a try. This is a linear regression problem, which is different from the classification problem you saw. I'll give you a hint. You all could layer should have only one neuron and no activation. In the next section, we'll start with a look at one solution to the assignment for step 1, and then start diving into why deep learning exists.